next speaker today, the third one, next in this morning is here, Ryuichi Fukuoka. Ryuichi is from uh, University of Maringá. He's now there working with Finsler metrics, and sometimes yes, sometimes no with symmetries, but with Finsler metrics. Today he will talk to us about the maximum of independent Finsler structures. So, Ruishi, thank you for coming, and the audience is yours.
Thank you for the presentation, Luis. Hi, all. I shared my slides on the chat, so for your convenience. So if you are interested, just click the address of the chat. Okay. I'd like to thank the organizer for the opportunity to talk about this subject with you. Okay. I will share my screen. This is a joint work with Hugo Murilo Rodrigues, and the question is, the objective is to show that the maximum of independent Finsler structures we can study with the Pontriaghi maximum principle. Okay. This work can be found at this address. It is already submitted. Okay. I'll give a short summary of the talk. I will define the Pontriaghi type C0 Finsler manifolds. In this talk, Finsler is the smooth version of Finsler, and C0 Finsler is the continuous version of Finsler, because there are two definitions for Finsler. Afterwards, we'll give the definition of extended geodesic field in the cotangent bundle. We'll define the maximum of independent Finsler structures. Okay. And we'll give a brief idea of the proof that, first of all, we can apply the Pontriaghi maximum principle in order to study this object. And second, that the geodesic field for this kind of object is a locally Lipschitz vector field. Well, I will give a very brief historic about the use of Pontriaghi maximum principle for the problem of minimizing path in geometry. This technique began to gain more adepts from the 1990s, okay? And there are some cases that this kind of technique is very well established nowadays. For instance, in Riemannian geometry, for the study of left invariant C0 sub-Finsler structures, they are very well established. I will talk just about a particular case of sub-Finsler cases, because there are other kind of structures that we can study with the Pontriaghi maximum principle, but I don't know very much about them, so I will concentrate myself in this talk about this kind of structures. Okay. Well, for Riemannian geometry, there are a usual way to study using, I will talk just PMP for Pontriaghi maximum principle. There's a usual way to study them. We consider orthonormal frame on the distribution of the sub-Riemannian manifold. Okay, this gives the required control system. I put here some references. This is a nice book about the subject. These are other references. I will not go into the details, okay? For left invariant C0 sub-Finsler structures only groups. There are other works. The first of them is this work, where the author studies the quasi-hyperbolic plane through the PNP. Okay. Here are other kind of works. And for these two types of problems, the way that we use PNP is very canonical. The control system that we use is quite canonical. But for other cases, there aren't a recipe, canonical control system to use in order to study them. I give some examples of the several ways to use the PNP to study specific problems here. Okay. And here I will begin with the basic definitions. First of all, what is an asymmetric norm on a finite dimensional real vector space? Well, asymmetric norm is a norm that doesn't satisfy necessarily the symmetry. So this is equivalent to say that the unit ball is a convex body with the origin in its interior. Okay. Now we define C0 Finsler structures, which are a generalization of Finsler structures. For those who doesn't know Finsler structures, for this talk, you can replace by Riemannian structures, Riemannian matrices, without loss of content. Okay. Here, C0 Finsler structure is a real-valued continuous function from the tangent bundle in such a way that its restriction to each tangent space is an asymmetric norm on each tangent space. Okay. And well, we are interested to study minimizing path for C0 Finsler structure. Okay, but notice that this guy is only continuous, then differential calculus aren't available to this kind of objects. So we can use the Pontriaghi maximum principle, but in order to use PNP, we need some kind of horizontal smoothness for F. So here we define the Pontriaghi type C0 Finsler manifolds. They are manifolds that satisfy the minimal requirements in order to apply the Pontriaghi maximum principle. So a C0 Finsler manifold is of Pontriaghi type at a point P if there exists a neighborhood U of P in such a way that we put a coordinate system on U. We call them x1 to xn, and this coordinate system induces a natural coordinate system on the tangent bundle. We call them in that way. And we have a control system given by a family of C1 unit vector fields, which we denote by in this way, in such a way that the control region is the Euclidean unit sphere, okay, in such a way that this control system satisfies the conditions required for the Pontriaghi maximum principle. Okay, the conditions are these one. These are the vector fields parameterized by the control U. This relationship is continuous, and this relationship is continuous also if we consider the partial derivatives. Okay, and we also demand that the relationship between the control region and the control system restricted to each tangent space is an homeomorphism from the Euclidean sphere onto the unit sphere on the tangent space with respect to F. Okay. And we say that F is of Pontryagin type on M if it is of Pontryagin type for every P. Okay. It's not difficult to prove that this kind of definition doesn't depend on the coordinate system that we choose. Okay. Now we want to study minimizing paths, more specifically minimizing paths parameterized by arc length. Okay. So the time minimizing problem is these problems that I told you now. It's the problem of study minimizing path parameterized by arc length. Okay. And what we'll do is to apply the PNP in this kind of problem in order to get the extended geodesic field on the cotangent bundle. Okay. So in order to define the extended geodesic field, we proceed as usual in PNP. Okay. We'll denote the cotangent bundle in this way. For every control, we define the respective Hamiltonian in the cotangent bundle of the coordinate neighborhood. Okay. And for every control, we define the Hamiltonian vector field. D sharp is with respect to the canonical simplex form on the cotangent bundle. We define the maximum function, which is the maximum of Hamiltonians when we vary the parameter u, the control u. This Cx alpha is the set of controls in such a way that the Hamiltonian reaches its maximum. Okay, and finally, we define the extended geodesic field in this way. The extended geodesic field is given by this guy where U maximizes the Hamiltonian at this point. Okay. Then the extended geodesic field is a relationship from the cotangent bundle into this guy in such a way that for every X alpha, it associates this guy. It's similar to, there are some similarities and some differences to the traditional geodesic field for Riemannian manifolds. Okay. Geodesic field is a session from here to here. Here we are in the cotangent bundle, and it's interesting to note what are the relationship between them. The canonical symplectic form gives a diffeomorphism between the tangent bundle and the cotangent bundle. In the Riemannian case, it's classical to define the geodesic field here, and now we use this diffeomorphism to define a geodesic field here. And the point is that the extended geodesic field is a kind of generalization of geodesic fields on a Finsler manifold on the cotangent bundle. Okay. Now, the theorem, the formalization is strong enough to guarantee that every minimizing path parameterized by arc length here is the projection of an absolutely continuous solution of the differential inclusion, okay, on M. Okay, and if you want to give a real generalization of the geodesic field in the Finsler case, we can consider the fiber-wise dual norm of F on the cotangent bundle. And this multi-evaluated map, okay, is a generalization of the geodesic spray on Finsler manifolds. Now we go into the maximum of independent Finsler structures. First of all, the definition of independent functions. Here, M is a differentiable manifold. X0 is a point here. We say that this set of smooth functions is independent on a neighborhood of this point if their differentials are linearly independent for every v. This implies that this set of functions can be computed in order to make a coordinate system on a neighborhood of x0. It's this kind of feature that we use in order to prove that the maximum of independent Finsler structures are suitable to be studied by PNP. Okay. And for the definition of maximum of independent Finsler structures, essentially a set of Finsler structures are independent if they are fiber-wise independent, or if we restrict the Finsler structures to each tangent space, they are independent in the sense above in the definition. For the question of time, I will give an idea of the proof that this is a C0 Finsler structure of Pontryagin type. Okay. The idea is very sensible. Here we have three Finsler structures. F1 is the red one, F2 is the green one, and F3 is the blue one. F1, F2, and F3 restricted to a tangent space, it gives a coordinate system in a neighborhood of this point. This is a point A. These are unit vectors. Then we have a coordinate system in a neighborhood of this point. Notice that this point is a point on the tangent bundle. So this kind of coordinate system goes not only in the tangent space, but in the whole neighborhood of the tangent bundle. Okay. Then we consider the constant vector fields with respect to this coordinate system, and we claim that this kind of construction of constant vector fields, it works in order to satisfy the requirements to be of Pontryagin type if we restrict these vector fields to the unit sphere of Fmax. Once given the F1, F2, F3, the unit sphere of the maximum is given by this smoothened cube. Okay, it is strongly convex. And if we restrict the construction of constant vector fields with respect to new coordinate system, it will work in order to prove that this kind of Fmax is a Pontryagin type C0 Finsler manifold. Okay. Now, okay. In order to give an idea that the extended geodesic field, the Lipschitz vector field on a neighborhood of a point of the cotangent space, we split the proof in two parts. The first one is the vertical part. Okay. Then, if you restrict the construction of the extended geodesic field to a tangent space, the relationship between the tangent bundle and the cotangent bundle is given by the inverse of the Legendre transform. Okay. and it's a classical result of convex analysis that this kind of relationships gives a Lipschitz type, a local Lipschitz type relationship between this guy and this guy. They are in the same tangent space, but they are different points. This Lipschitz type relationships is due to the strong convexity of the sphere. And also using convex analysis, you can make a kind of identification between different cotangent spaces, okay? Essentially, let's take up here a part of a unit sphere here, we are here in the tangent space. Here we are in other tangent space. Okay, so here we have F1, the sphere of F1, sphere of F2, sphere of F1, sphere of F2. And we want to define a map between these guys. Okay. If this guys is a functional, is a differential of F1, for instance, it goes onto the differential of F1. If this guy is a differential of F2, it goes to the differential of F2. And there's a problem here where the maximum coincides, okay? And in these cases is a result of convex analysis that if we take the differential here, differential of F1 here and the differential of F2 here, all the guys that are here are convex combination of these guys, and all the guys that are here are convex combination of this guy. Then we take the convex combination to the respective convex combination, and the idea is that this kind of geometric construction works in order to prove that the extended geodesic field is a locally Lipschitz vector field. Okay. Thank you for your attention.
Thank you, Ryuichi. Thank you. Any questions? Leonardo? No.
No.
Wow. People are hungry already. Here it's lunchtime for us. So let's thank Ryuichi again. Thank you very much, Ryuichi, for giving us a talk.
Thank you.